Hello everyone, Rocket Mathematics here, and today we're going to speak about stochastic analysis and more specifically for sigma algebras, measurable and probability spaces. These concepts are necessary for converting abstract probability theory into formal mathematical definitions. Before getting deeper into stochastic analysis, we should introduce some basic concepts taken from measure theory and functional analysis. We are going to begin by defining the sigma algebra. A sigma algebra F of a set X is a collection of subsets of X with the following properties. The empty set and X are contained in the sigma algebra F by definition. If A belongs to F, then its complement also belongs to the sigma algebra F. If A1, A2, A3, and so on are contained in the sigma algebra F, then the union of all these sets are also contained in the sigma algebra F. Let's see an example of a sigma algebra on the set X which contains the numbers 1, 2, and 3. A sigma algebra F with respect to the set X can contain the set X, the empty set, the singleton with element the number 2, and the set which contains the number 1 and 3. The smallest sigma algebra is quite useful in probability theory since it can be correlated with random variables. We're going to see it further in our videos. The smallest sigma algebra that can contain the set A is symbolized with sigma A. Sigma A contains the empty set omega, set A, and its complement AC. Now we're going to define the Borel algebra. A sigma algebra can also be defined for the set of real numbers R. In this particular case, the sigma algebra is called Borel algebra. Borel algebra of the set of the real numbers is the small sigma algebra which contains all the intervals from -infinity to x subsets of the real axis. The elements of the Borel algebra are also called Borel sets. The definition of Borel algebra can be generalized into the n-dimensional set of real numbers. Knowing what sigma algebra is, we can now define the measurable space. Measurable space is simply the pair X and F, where F is sigma algebra on the set X. Similarly, the pair which contains the set of real numbers and its Borel algebra is a measurable space. Now we are going to define the probability measure. A probability measure maps a set to a specific number. The probability measure takes values in the closed interval from 0 to 1. More formally, P is a probability measure in the measurable space X and F, where P maps a set of the sigma algebra F to a specific number between 0 and 1. The probability of the event, which can be described with the empty set, is 0, and the probability of x is equal to 1. Moreover, if A1, A2, A3, and so on are contained in the sigma algebra F and the sets are pairwise disjoint, then the probability of the union of all these events is equal to the sum of the individual probability of each event. We should point out that if the probability of x does not equal 1, then P is not a probability measure and it's called simply measure. Finally, we're going to define the probability space. The triple X, F, and P is called probability space, where F is sigma algebra on X and P the probability measure. Probability space will be used later to describe stochastic processes and random variables. Thanks for your valuable time.